Hello students, welcome back to session 2 of linear transformations. So here in this class we will study what will be the rank, nullity of a linear transformation, Sylvester's law and many more like the eigenvalues of a linear transformation, eigenvectors and the corresponding theorems. Okay, suppose V is a finite dimensional vector space over a field F, okay, and let T be an element of A of V. We define the rank of the transformation T as the dimension of the range of T. Dimension of the range of T, that is, what is the range of T? Range of T is T of V is the range. So dimension of range of T, that is denoted by R of T, and the nullity of T is the dimension of the kernel of T or dimension of the null space of T, and it is denoted by neta of T. Okay, so rank and nullity. So rank and nullity are related to the dimension of the vector space, that is given by the Sylvester's law. So this says if T is an element of A of V, then rank of T plus nullity of T will be equal to the dimension of V, is equal to the dimension of the vector space V. So let us prove this now. So for this, let V be the dimension of n. Let V be of dimension n. Okay. So now we know that the null space of T is a subspace of V, or kernel of T is a subspace of V. Therefore, let dimension of kernel of T, it's a subspace means it has some fixed dimension. Let the dimension be K. Its dimension is K means there are K number of basis elements for kernel of T. Let U1, U2, etc. Uk be the basis elements of kernel of T. Now, these are the basis elements of kernel of T means these are the elements of, they are linearly independent in kernel of T. Okay, they are linearly independent in kernel of T means they are linearly independent in the vector space V, because these are elements of the vector space V itself. So now we have a K number of linearly independent vectors in V. So you know that every linearly independent set in V can be extended to form a basis. But the dimension of the vector space, they were given to be n. So here we have K number of linearly independent vectors. So I need to add n minus K number of vectors so that these can forms a basis of V. So I will add V1, V2, etc. Vn minus K to the existing basis U1, U2, etc. Uk to form a basis of V. Okay. So U1, U2, etc. Uk, V1, V2, etc. Vn minus K is a basis of the vector space V. Thus, any vector in V can be written as linear combination of these basis elements. So say X is an element of V implies X can be written as summation C1 U1, C2 U2, etc. Ck Uk, Ck plus 1 V1, and so on. Total elements is Cn Vn minus K. Now you apply T for this above vector X. So this implies T of X is equal to T of the right hand side term. Since T is linear, this can be written as C1 into T of U1 plus C2 into T of U2, etc. Ck into T of Uk plus Ck plus 1 into T of V1, and so on, Cn into T of Vn minus K. Okay, this implies, but look here, now U1, U2, etc. Uk are basis elements of kernel of T, means these belongs to kernel of T. If these belongs to kernel of T, then what will happen? T of U1 is 0, T of U2 is 0, etc. T of Uk is 0. Okay, therefore T of X will become, T of X is equal to, say, C of X becomes, T of X becomes C1 0, etc. up to K numbers, it is 0 plus Ck plus 1 T of V1 plus Ck plus 2 T of V2, etc. Cn into T of Vn minus K. Thus the element T of X, where it lies? It lies in the image space T of V. Okay. Thus T of X belongs to T of V can be expressed as a linear combination of n minus k vectors t of v1, t of v2, etc. t of n minus k. Therefore, these n minus k vectors definitely span the image space t of v, which is the range of t, okay, which is the range of t. So therefore, also these vectors we can found to be linearly independent. Now they span t of v as well as they are linearly independent, that we have shown it here. So they are linearly independent means they form a basis of the range space t of v. Therefore the dimension of t of v is what? How much? N minus k, which is n is dimension of v minus k means dimension of kernel of t. Therefore range of t if you will be equal to dimension of t of v is what? Range of t is equal to dimension of v minus dimension of kernel of t is nullity of t. Range of t means what? This implies dimension of v is equal to range of t plus nullity of t. Okay, so that is equal to r of t plus net of t. Okay, range of t, or sorry, this is the dimension of t of v is rank of t, rank of t. So this is our rank of t and plus nullity of t. So dimension of v is equal to rank of t plus nullity of t. Right? This is the Sylvester's law. Now let us take one example based on the Sylvester's theorem or Sylvester's law. Say this example gives what will be the range, rank, kernel and nullity of a linear transformation. So I will take the linear transformation T to be from R3 to R3, V is R3 here, given by T of xyz is equal to x plus z, x plus y plus 2z, 2x plus y plus 3z. Okay. Now, so we need to find the range, rank, kernel and the nullity. So for this, let xyz be any arbitrary element of kernel of T. So if this is any element of kernel of T means T of that element, T of xyz is definitely, this is equal to 0 by the definition of kernel of T. Now T of xyz means they were given to be x plus z, x plus y plus 2z, 2x plus y plus 3z is equal to 0. This implies x plus z is 0, x plus y plus 2z is 0, 2x plus y plus 3z is 0. So solving for this, solving for xyz, we get x is to be minus z and y is to be minus z. X is minus z, y is z. So x and y depends on z only. Therefore kernel of T becomes set of all x such that x comma is what kernel of T is, x means minus z z, or x into 1 1 minus 1, 1 1 minus 1 for every element x belongs to R. Okay, kernel of T is this. Now kernel of T is spanned by a single element 1 1 minus 1. Therefore the dimension of kernel of T is 1. Dimension of kernel of T is nullity of T, that is equal to 1. Okay, so we find what will be the kernel of T and we find the what is the dimension of kernel of T, that is nullity of T. Okay, next, and look here, x plus y, x plus z plus x plus y plus 2z plus 2x plus y plus 3z is equal to, this can be written as x plus 0 plus z, x plus y plus 2z, 2x plus y plus 3z. So this can be written as x comma 2x plus 0 comma y, next is z comma 2z 3z. So if you add this, you get the same. Okay, so x is common, x into 1 1 2, y into 0 1 1, z into 1 2 3. Now look here, this is T of v, T of x, or the transformation T, this is equal to T of xyz is equal to, this can be written as the linear S combination of 1 1 2, 0 1 1 and 1 2 3. Therefore this element is in the range of T, that element is spanned by these three vectors. Okay, therefore range of T is spanned by 1 1 2, 0 1 1, 1 2 3. Now they span by three vectors means since 112 plus 0 1 1, 112 plus 0 1 1 is equal to 1 2 3 means, so one vector is a linear combination of preceding vectors. Therefore this set is linearly dependent. They are spanning the range of T, but they are linearly dependent. So range of T definitely is less than or equal to 2, less than or equal to 2, because one vector other vector is depend on the previous two, linear sum of previous two vectors. Therefore dimension of range of T is maximum, it is 2. Now you can check that the vectors 1 1 2 and 0 1 1 definitely they are linearly independent. They are linearly independent. So from this spanning set I have chosen the two vectors which also spans range of T and also they are linearly independent. Therefore the dimension of the range of T is what? Only these are spanned by, these becomes the basis elements 1 1 2 and 0 1 1. Therefore dimension of range of T is 2, that is denoted by rank of T. So here dimension of V is how much? Dimension of V is here 3, rank of T is 2 and nullity of T is 1. Therefore 3 is equal to 2 plus 1 and the above theorem is verified here. Okay. Next let us take up one problem. Suppose T belongs to A of V and T satisfies some polynomial, say f of x belongs to f of x. Then prove that the minimal polynomial for T over f divides f of x. So if T belongs to A of V and if T satisfies f of x, then minimal polynomial of T divides this polynomial f of x. Okay. So for this, let P of x be the minimal polynomial of T. P of x be the minimal polynomial means P of x also belongs to the polynomial field f of x. Now f of x also belongs to f of x, P of x also belongs to f of x, which is the polynomial field. But division algorithm holds good in f of x, that we have proved in rings classes, extension fields classes. Therefore by division algorithm in f of x, what will happen? There exist two polynomials, say q of x and r of x in f of x, such that the polynomial f of x can be written as q of x into p of x or p of x into q of x plus r of x. What is r of x? Is the remainder where r of x is 0 or degree of r of x is less than degree of p of x. Okay. Now T satisfies f of x imply what? F of t is 0. Therefore 0 is equal to f of t, that's equal to p of t into q of t plus r of t. But p of t is 0 because p of x is the minimal polynomial for t. Therefore f of this is equal to r of t, means r of t is 0, means t satisfies r of x. If r of x is 0, then no problem. Okay, every transformation satisfies the 0 polynomial. But if r of x is not the 0 polynomial, then what will happen? T is satisfying a polynomial r of x which is of degree less than that of p of x, which is a contradiction because p of x is the minimal polynomial for t, means it is the smallest polynomial, it is the polynomial of smallest degree satisfied by t. Okay, therefore r of x cannot be 0, r of x should be 0. R of x should be 0 means, sorry, r of x should be 0 means what about f of x? F of x becomes p of x into q of x. Now if f of x is being written as p of x into q of x means what? Definitely p of x divides f of x. Okay, 6 can be written as 2 into 3 means 3 divides 6, 2 also divides 6. So which implies p of x divides f of x. Thus the minimal polynomial of a transformation t s divides the polynomial satisfied by t. Okay, minimal polynomial divides the polynomial satisfied by t. Next is, so you observe this theorem. So if t1 and t2 are unit transformations or linear operators on V, then rank of alpha into t1 is alpha into rank of t1. This is alpha into rank of t1 for all alpha belongs to f, where alpha is non-zero. Okay, and mod of r of t1 rank of t1 minus rank of 2 is always less than or equal to rank of t1 plus t2, but this is certainly less than or equal to rank of t1 plus rank of t2. Okay, here r of t denotes the rank of t. Okay, so you write this result in your assignments. Okay, next let us take up the other lemma. So this lemma says if V is a finite dimensional vector space over a field F, then for the transformation S comma T belongs to A of V, rank of Ts is less than or equal to rank of T, rank of St is also less than or equal to rank of T, and rank of St is same as rank of Ts, and that will be equal to rank of T if S is regular in A of V. For S is regular in A of V. So let us prove one by one. Now first one, clearly S of V is contained in V because S is a mapping from where to where. S is a transformation from V to V, means the image of V under S is definitely is in V only. You apply T for this. T of S of V is contained in T of V. This can be written as T into S of V is contained in T of V. This implies dimension of T into S of V is certainly less than or equal to dimension of T of V. Dimension of T into S of V means rank of T into S is less than or equal to rank of T. Okay, so we have proved the first result. Rank of T into S is less than or equal to rank of T. Second one, say suppose rank of T is M. Suppose that rank of T is M. That is, rank of T means dimension of T of V is M. Now dimension of T of V is M means what? There are M number of basis elements for T of V. So let those basis elements be say W1, W2, etc. Wm. If these are basis elements for T of V, then S into T of V is spanned by which elements? S of W1, S of W2, etc. S of Wm. So S into T of V is spanned by these same M elements, S into W1, S of W2, etc. S of Wm. Therefore dimension of St of V is how much? They are spanned by these M vectors, means which is definitely less than or equal to M. Okay, so this implies therefore rank of St is less than or equal to M, which is the dimension of T of V, that's equal to rank of T. So this implies rank of St is also less than or equal to rank of T, which is 2. Okay, thus we have proved rank of St is less than or equal to rank of T. So let's come to the third condition. So if S is regular in A of V, S is regular means S inverse exists. Inverse for S definitely exists. Then if S is regular means what will happen? It is onto. S is regular means if and only if it is onto, we have proved this result. Therefore it is onto means S of V is equal to V itself. S of V is equal to V. Therefore what will happen? T into S of V is T of S of V is T of S of V. S of V is V here only, so this is equal to T of V. This implies dimension of T into S of V is what? This is equal to dimension of T of V. So dimension of T into S of V means rank of T into S is equal to rank of T. Okay. On the other hand, if T of V has basis elements W1, W2, etc. Wm as basis, then the regularity of S implies that what? S of W1, S of W2, etc. S of Wm are linearly independent. Okay, they are linearly independent. Since these are spanning S into T of V, therefore they form a basis of S into T of V. They form a basis of S into T of V means what? Dimension of St is the dimension of S into T of V, that is rank of St is equal to dimension of S into T of V. So this is equal to dimension of T of V itself. T of V itself. Dimension of T of means rank of T. Therefore rank of St is equal to rank of T. So already we have shown, say rank of Ts is equal to rank of T. Now we have shown that rank of St is also rank of T. Thus rank of St is same as rank of T, that's equal to rank of T into S. So we have proved the three conditions related to the rank of a linear transformation. So you know what's meant by eigenvalues and eigenvectors in matrix theory. Okay. So here we define the eigenvalues and eigenvectors of a linear transformation. So in the next section we will discuss what's the relation between the matrices and the set of linear transformation, that we will discuss in the next class. So here, say let us define what is meant by an eigenvalue and eigenvector. Okay. So here in this section we will consider V always to be a finite dimensional vector space. Okay. Say if T belongs to A of V, then a scalar lambda in E of is called an eigenvalue of T if there exists a non-zero vector V in V such that T of V is equal to what? Lambda times V. So this definition, you know it. Okay. So any non-zero vector V belongs to V such that T of V is equal to lambda into V is called the eigenvector of T corresponding to the eigenvalue lambda. Okay. Here lambda is called the eigenvalue and V is called the corresponding eigenvector. So note that if V belongs to V is an eigenvalue of T, if V belongs to V is an eigenvector of T, this is not value, eigenvector. If V belongs to V is an eigenvector of T, then V cannot corresponding to more than one eigenvalue of T, because if you assume that V corresponds to eigenvalues, then what will happen? Okay. So lambda 1 into V is equal to lambda 2 into V. Okay. So this implies V cannot be 0 because it is an eigenvector. Therefore lambda 1 must be equal to lambda 2. Okay. Thus any eigenvector will corresponding to as only one eigenvalue. So you can use the terminologies like characteristic roots and characteristic vectors instead of eigenvalue and eigenvectors. Okay. Now you will take up this result. Suppose T belongs to A of V and lambda is a scalar. Then this lambda is called an eigenvalue of T if and only if lambda I minus T is singular, or the transformation T minus lambda is singular. Okay. So lambda is an eigenvalue if and only if the transformation T minus lambda is singular. Okay. So for this, suppose lambda is an eigenvalue of T, then by definition what will happen? There exists a non-zero vector V in V such that T of V is equal to lambda times of V. This implies what? Lambda V minus T of V is equal to 0, or in other words lambda into I. So lambda minus T or lambda into I minus T of V is 0. So for the non-zero vector V in V, lambda I minus T of V is 0 means then by the definition lambda I minus T is singular. This we have proved it as a result theorem. Okay. So T is singular if and only if it maps non-zero vector to 0 vector, that we have proved in the last class. So according to that, lambda I minus T is singular. Lambda I minus T is singular means what you can say? Say this is the required thing. Lambda is an eigenvalue if and only if, lambda is an, we have assumed that lambda is an eigenvalue and we have proved lambda I minus T is singular. On the other hand, or conversely, let us take lambda I minus T is singular. So lambda I minus is singular. Then what will happen? By definition there exists a non-zero vector V in V such that lambda I minus T of V is 0. This implies lambda of V minus T of V is equal to 0, or this implies T of V is equal to lambda times of V. Then by definition lambda is an eigenvalue of T. Thus lambda is an eigenvalue of T if and only if lambda I minus T is singular. Okay. Now say let us discuss the next result. Okay. Suppose lambda 1, lambda 2, etc. lambda n are distinct eigenvalues of the transformation T belongs to A of V, and v1, v2, etc. vn are the corresponding eigenvectors of T. Okay, these are the eigenvectors corresponding to the eigenvalues lambda 1, lambda 2, etc. lambda n. Then these eigenvectors are linearly independent over F. Okay, so according to this theorem, the eigenvectors are linearly independent. So let us prove this by a method of induction. So suppose the dimension of the vector space is n. Okay, so if you want to prove this by induction, means suppose n is equal to 1. If n is equal to 1, then we have only one vector v1, say v1, and any non-zero vector v1 is definitely linearly independent. Okay, and so the theorem is proved. Suppose that the theorem is true for n minus vectors, means there are n minus 1 distinct eigenvalues, and v1, v2, etc. vn minus 1 are corresponding eigenvectors, and they are linearly independent. So we need to prove that all the n vectors v1, v2, etc. vn are linearly independent. So for this, you consider the relation c1 v1 plus c2 v2, etc. cn vn is equal to 0, where ci's are scalars. Now to show these are linearly independent, what we have to show? Each of these scalar coefficients ci's must be equal to 0. We will show this. Now you apply the transformation T onto the expression 1. What do you get? If you apply T, since T is linear, directly I can write c1 into T of v1 plus c2 into T of v2, etc. cn into T of vn is equal to T of 0. T of 0 is 0 itself. So this is equal to c1 into, what is T of v1? So v1 is the eigenvector corresponding to the eigenvalue lambda 1. Therefore c1 into lambda 1 v1 plus c2 into lambda 2 v2, etc. cn into lambda n vn. So you call this by number 2. Now you multiply the equation 1 by lambda 1. Multiply the equation 1 by lambda 1. Then we get, say, c1 into lambda 1 v1 plus c2 into lambda 1 v2, etc. cn into lambda 1 vn. You call this by number 3. Now you subtract 3 from 2. Okay, then we get, so first expression get cancelled, c1 lambda 1 v1, it is common in both 2 and 3, therefore it get cancelled. So the other terms are c2 into lambda 1 minus lambda 2 into v2 plus c3 into lambda 1 minus lambda 3 into v3, etc. cn into lambda 1 minus lambda n into vn is equal to 0. Now these eigenvalues are distinct. Distinct means lambda 1 minus lambda 2 is not equal to 0, lambda 2 minus lambda 1 minus lambda 3 is not equal to 0, etc. lambda 1 minus lambda n is also not equal to 0. Now you come to this expression. Now this is an expression like linear combination of v1, v2, etc. vn is equal to 0. How many vectors are there here? n minus 1 vectors. But we have assumed that the theorem is true for the dimension n minus 1. The theorem is true for the dimension n minus 1 means what? These n minus 1 vectors are linearly independent. These are linearly independent means what will happen? Each of these scalar coefficients, what is the coefficients? Ci into lambda 1 minus lambda I, Ci into lambda 1 minus lambda I is equal to 0, or in other words c2 into lambda 1 minus lambda 2 is 0, c3 into lambda 1 minus lambda 3 is 0, etc. cn into lambda 1 minus lambda n is 0. Okay, but lambda is are, as I said, lambda is are distinct, so these cannot be, lambda 1 minus lambda I cannot be equal to 0 for I takes the value 2, 3, etc. up to n. Now, so these cannot be 0, and Ci into lambda 1 minus lambda I is equal to 0 is what? These are all elements of field F, but a field has no zero divisors, means multiplication of two non-zero elements cannot be equal to 0. So this lambda 1 minus lambda 2 is not 0, but C2 into this is 0 means what we have to? Yes, we will arrive at C2 must be 0 because F has no zero divisors. Therefore, C2 is 0, C3 is 0, etc. Cn is equal to 0. If C1, C2, C2, C3, etc. Cn are all zeros, then by the expression 1, what do you get? C1 into V1 is 0. But V1 cannot be 0 because V1 is a eigenvector. So C1 into V1 is equal to 0 means C1 is equal to 0. Now C2 is 0, C3 is 0, etc. Cn is 0 and as well as C1 is also 0. Therefore from the expression 1 we can say that V1, V2, etc. Vn are linearly independent. Okay. Therefore the eigenvectors are linearly independent. Okay. Now say this result has two important corollaries. So the corollary one says, look here, if dimension of V is equal to n and T belongs to A of V, then T can have at most maximum n distinct eigenvalues in F. If the dimension of vector space is n and T is an operator on V, then T can have at most n distinct eigenvalues in F. Now since the dimension of V is n, okay, any set of linearly independent vectors in V can have at most how many elements? N elements. Okay. So dimension of V is n means any set of linearly independent vectors in V contains at the most how many elements? N vectors only. N vectors only. But by the above theorem, any set of distinct eigenvalues gives rise to corresponding linearly independent eigenvectors. Means what will happen? The eigenvectors are linearly independent. Here the dimension of the vector space is n and okay, according to above theorem, the eigenvectors are linearly independent. So how many maximum eigenvectors exist here? So n is the only possibility, because so if more than n means it exceeds the dimension of the vector space. So if it is an eigenvector means it is linearly independent. Since the dimension of vector space is n, there are at the most n distinct eigenvalues. N distinct eigenvalues for T. Okay. Next, the next corollary says, look here. Suppose the dimension of the vector space V is n and T belongs to A of V as n distinct eigenvalues in F. Okay. Then there exists a basis of V consisting of eigenvectors of T. Means if dimension of V is n and T belongs to A of V as n distinct eigenvalues, then basis of V contains these eigenvectors. Okay. So let's prove this. Let lambda 1, lambda 2, etc. lambda n be the n distinct eigenvalues of T. If these are the n distinct eigenvalues means there exists a corresponding eigenvectors, say V1, V2, etc. Vn are the corresponding eigenvectors. But by the previous theorem, these eigenvectors are linearly independent. Since dimension of V is n, these linearly independent vectors itself forms a basis of V. Okay. So you know that if the dimension of the vector space is n, then any set of n linearly independent vectors forms a basis of V. That theorem you have proved. Okay. Since these are linearly independent vectors, these linearly independent vectors, that is these eigenvectors itself forms a basis of the vector space V. Okay. So that is there is a basis of V over F consisting of eigenvectors of T. Right. So now say let us take up small lemmas, two simple results. Say suppose lambda belongs to F is an eigenvalue of T. Then for any polynomial f of x belongs to f of x, f of lambda is an eigenvalue of the transformation f of t. So look here, if lambda belongs to f is an eigenvalue of t, then for any polynomial f of x belongs to f of x, f of lambda is an eigenvalue of f of t. Okay, we have to prove this. Say let lambda belongs to f is an eigenvalue of t. If lambda is an eigenvalue of t, imply what? There exists some non-zero vector v in v such that t of v is equal to lambda times v. This v is called the corresponding eigenvector. Now t square of v is what? T of v. So t of v is what? Lambda times of v. Since t is linear, lambda into t of v. Again t of v is what? Lambda into v. So lambda into lambda means lambda square of v. Therefore t square of v is what? Lambda square of v. Thus t cube of v is lambda cube of v, and so on. In general, any tk of v is lambda power of k or lambda power of k into v for any positive integer k. Now say you take f of x to be the polynomial, say like f of x is equal to say a0 plus a1x and so on an x power of n, where a's are scalars in f. Scalars belongs to the field f. Okay, now f of t is what? a0 plus a1t, a2t square and so on an into t power of n. So that f into t of v is what? The vector v, if you apply vector v here, so a0 into v plus a1 into t of v plus and so on an into tn of v. Now a0 into v plus a1 into t of v is what? Lambda of v, and so on an into tn of v is lambda power of n into v. So this is a0 plus a1 lambda and so on an into lambda power of n of v. What is this? This is nothing but f of lambda of v. This implies f into t of v is equal to f into f of lambda of v. This implies f of t of v minus f of lambda of v is equal to 0. Now f of t is also a transformation. Okay, it is a polynomial in t, means what? This is also an element of a of v. Okay, so that is equal to, this is equal to 0 means what? You can say f of t minus f of lambda is a singular transformation. Okay, f of t minus f of lambda is singular means what you can declare? F of lambda is an eigenvalue of f of t. Okay, thus if lambda is an eigenvalue of t, then f of lambda is an eigenvalue of f of t. Okay, next, so look here. So here, suppose lambda belongs to f is an eigenvalue of transformation t belongs to a of v. Then this lambda eigenvalue lambda is a root of the minimal polynomial of t over f. Means the eigenvalues are the roots of the minimal polynomial of a transformation. Okay, this is a very important result. The eigenvalues are the roots of the minimal polynomial. Okay, let p of x be the minimal polynomial of t. Then by definition of a minimal polynomial, p of t is 0. Okay, or p of x is the polynomial of smallest degree satisfied by t, so that is p of t is 0. Now they were given lambda is an eigenvalue of t. Now just now we have proved if lambda is an eigenvalue of t, then p of x is a polynomial. Therefore p of lambda is an eigenvalue of p of t. Now p of lambda is an eigenvalue of p of t implies what? P of t of v is equal to p of lambda of v. But p of t is 0 because t satisfies p of x. Therefore this is equal to p of lambda of v. Now v is a non-zero vector, it's an eigenvector, so it's non-zero, so v is not equal to 0. Therefore what is the possibility? P of lambda is equal to 0. P of lambda is 0 means what? Lambda is a root of p of x. Lambda is a eigenvalue that is a root of the minimal polynomial p of x. Therefore the eigenvalues are the roots of the minimal polynomial. Okay, so the eigenvalues are the roots of the minimal polynomial. Now let us take the last result of this class. Say suppose s and t belongs to a of v, means s and t are linear operators on v. Suppose s is regular, and suppose s is regular, then what will happen? The transformation t and the transformation s t s inverse, this is a single transformation, have same minimal polynomial. Means if s and t are elements of a of v, and if s is regular means invertible, so inverse exists. Okay, so and if s is regular, then t and s t s inverse have same minimal polynomial. Okay, so let p of x is equal to a0 plus a1x etc. an x power of n be the minimal polynomial of t. Okay. So then by definition what will happen? P of t is 0. Okay. Now st s inverse whole square can be written as st s inverse into st s inverse. So this can be written as, since it is an a of is an algebra, I can use the property of an algebra. So this is equal to s into t into s inverse into s. I will group this into t into s inverse. Now s is regular means what? Inverse exists. So s inverse into s is I, identity transformation. So I into any transformation is itself. So s into t into I into t means s into t square into s into t square into s inverse, means st s inverse whole square is s t square s inverse. Similarly, for a very positive integer k, st s inverse whole power of k is what? S into t power of k into s inverse. Okay. Now you come to this. Now p of st s inverse is what? P of x is a minimal polynomial of t. Now p of st s inverse is what? a0 plus a1 into st s inverse plus a2 into st s inverse whole square and so on. The last element is an into st s inverse whole power of n. Now a0 into no element is present here, so I can write the transformation I. I can be replaced by s into s inverse. So a0 into s inverse plus a1 into st s inverse plus a2 into s t square s inverse and so on, an into s t power of n into s inverse. So this can be written as s into a0 plus a1t plus a2t square and so on, an into t power of n into s inverse. So I group like this. So s into, what is this? This is nothing but p of t into s inverse, but p of t is 0. Therefore this term, right hand side term is equal to 0. What? P of st s inverse is 0 means what? P of x is also a minimal polynomial of st s inverse. P of x is also a minimal polynomial of st s inverse. Thus yes, both the transformation s, so therefore the transformation t and st s inverse have the same minimal polynomial, which is taken to be p of x. Okay. So if s comma t belongs to a of v and if s is regular, then both the transformation t and st s inverse have the same minimal polynomial. These are the few results discussed in this class. Okay. Thank you very much.